In the familiar world, the world of our senses, objects possess a comforting and absolute certainty. A stone, resting on a flat expanse of earth, has a definite location. It occupies a specific volume of space, its dense granitic structure displacing the air around it with unambiguous boundaries. One can measure its mass, a consistent value of 13 kilograms, and trace its edges with a fingertip, feeling the cool, rough texture that signals its undeniable presence. It is a thing of substance, a monument to the logic of the tangible. Its past is a linear history of geological compression and erosion, and its future is one of slow, predictable decay under the patient forces of wind and water. This is the universe of common sense, a realm governed by intuitive laws where an object cannot be in two places at once, where a barrier is absolute, and where the influence of one thing upon another is constrained by the space that separates them. This entire edifice of understanding, however, is an illusion of scale. It is a magnificent and useful approximation, a consensus achieved by a population of underlying events so numerous and so rapid that they mimic the quality of permanence. The solidity of the stone is not a fundamental property, but a statistical artifact. Its unyielding presence is a story told by trillions upon trillions of fleeting quantum interactions, a story that, when examined in its native language, dissolves the very concepts of location, substance, and certainty. The universe, at its most granular level, does not speak in the prose of definite statements, but in the poetry of possibility. Beneath the veneer of this apparent solidity, a descent into the heart of the stone's matter begins a journey away from the familiar. The crystalline lattice of silica and feldspar, a repeating and rigid geometry at the macroscopic scale, dissolves into a vibrating architecture of molecules. These molecules, in turn, give way to their constituent atoms, vast realms of emptiness punctuated by minuscule concentrations of mass and charge. Here, at a scale 100,000 times smaller than the atom itself, lies the nucleus, a dense cluster of protons and neutrons bound by forces of incomprehensible strength. Surrounding this core, in the vast and lonely expanse of the atom, exist the electrons. Early attempts to map this realm envisioned it as a miniature solar system, with electrons orbiting the nucleus like planets around a sun, held in place by the pull of electric charge. This model, while a helpful first step, retained a classical comfort that reality itself refused to honor. The electron is not a simple point-like particle following a predictable, elliptical path. It cannot be pinned down to a specific trajectory. Instead, its existence is more accurately described as a cloud, a diffuse haze of probability. This is not a cloud of dust, nor a physical smear of the electron's substance, but a mathematical and conceptual cloud representing the likelihood of the electron's presence. In any given instant, the electron is not at a single point within this cloud, it simultaneously inhabits all points, with varying degrees of probability. Its identity is smeared across a volume of space, a ghostly potentiality that only resolves into a definite location upon interaction. The very question, where is the electron right now, becomes a meaningless inquiry, a linguistic relic from a larger world that does not apply in this deeper, more mysterious stratum of existence. This fundamental ambiguity of the electron's nature is most starkly and famously revealed in the double-slit experiment, a deceptively simple arrangement that systematically dismantles the foundations of classical intuition. If one were to fire a stream of macroscopic particles, like tiny pellets, at a barrier containing two parallel vertical slits, the result would be predictable. The pellets that pass through the slits would accumulate on a detector screen behind the barrier, forming two distinct bands directly corresponding to the openings. This is the behavior of particles. If one were to instead direct waves, perhaps ripples on the surface of water, toward the same two slits, a different pattern would emerge. As the waves pass through both slits simultaneously, they create two new, expanding wave fronts. These fronts interfere with each other, where the crest of one wave meets the crest of another, they reinforce, creating a larger wave. Where a crest meets a trough, they cancel each other out. The result on the detector screen is not two simple bands, but a characteristic interference pattern of many alternating bright and dark stripes, evidence of the wave's self-interaction. Now, consider an electron. Fired one at a time, so that there is no possibility of interaction with other electrons, it arrives at the detector screen as a single, localized dot, a particle. Yet, as thousands upon thousands of these individual electrons are fired, one by one, an astonishing pattern begins to emerge from the accumulation of these discrete impacts. It is not two bands. It is the unmistakable interference pattern of a wave. This outcome forces a conclusion that defies all common sense: each individual electron, traveling alone, must have passed through both slits simultaneously as a wave, interfered with itself, and only then resolved into a particle at a single point on the screen. It is both a particle and a wave, holding these contradictory identities not in sequence, but in a state of unresolved potential. The profound strangeness of this wave-particle duality deepens further when one considers the role of observation. Faced with the seemingly impossible conclusion that a single electron passes through two separate places at once, a logical next step is to try and watch it, to determine which slit the particle actually traverses. One might imagine placing a tiny detector, a metaphorical flashlight, at one of the slits, designed to register the electron's passage. When this experiment is performed, the detector indeed registers the electron passing through one slit or the other, but never both. The electron is now behaving as a well-mannered particle, following a single, definite path. But in the process of this observation, something fundamental is altered. When one looks at the final pattern accumulating on the screen behind the barrier, the interference pattern has vanished. In its place are two simple bands, exactly as one would expect from classical particles. The very act of measuring the electron's path, the act of asking the question, "Which way did you go?" forces it to abandon its wave-like nature. It is as if the universe holds its quantum secrets in a delicate, suspended state, and the clumsy touch of measurement compels it to choose a single, classical reality. This is not a simple mechanical disturbance, like a clumsy probe knocking the electron off course. It is a fundamental principle. The information about the electron's path and the interference pattern are complementary properties, to no one is to erase the other. Reality itself appears to be conditional, its expression dependent on whether or not it is being interrogated. The unobserved system evolves as a wave of possibilities, while the observed system is precipitated into a single actuality. This state of existing in multiple states at once is formalized in the concept of superposition. Before a measurement is made, a quantum system like an electron does not possess a definite property, such as position or spin. Instead, it exists in a superposition of all its possible states simultaneously. It is not in position A or position B, it is in a weighted combination of A and B. This is not a statement of ignorance about the electron's true state, but a complete description of the state itself. The electron's wave-like nature is described by a mathematical object known as the wave function, which encapsulates all these possibilities and their associated probabilities. The act of measurement is what causes this wave function to collapse, instantaneously and randomly, into one of its constituent states. The probability of it collapsing into any particular state is determined by the mathematics of the wave function, but the specific outcome of any single measurement is fundamentally unpredictable. Quantum mechanics does not offer the deterministic certainty of classical physics, where knowing the initial conditions of a system allows for the precise prediction of its future. Instead, it offers only probabilities. It can tell you with great accuracy that if you measure the position of an electron 1,000 times, a certain percentage will be found in one region and a certain percentage in another, but it can never tell you where the next electron will be found. At its most fundamental level, the universe appears to operate not on the clockwork determinism of cause and effect, but on the role of a cosmic die. The classical world's predictability is an emergent property, the result of averaging over an immense number of these individual probabilistic events, where the law of large numbers smooths out the underlying quantum randomness into the reliable behavior of the objects we experience every day. The probabilistic nature of the quantum world gives rise to phenomena that are not merely counterintuitive, but classically impossible. One such phenomenon is quantum tunneling. Imagine a ball rolling toward a hill. If the ball does not have enough kinetic energy to reach the top of the hill, it will roll partway up and then roll back down. It will never, under any circumstances, simply appear on the other side. The Hill represents an energy barrier that, in a classical system, is insurmountable without the requisite energy. In the quantum realm, however, the rules are different. When a particle, such as an electron or an atomic nucleus, encounters an energy barrier that it classically lacks the energy to overcome, there exists a small but non-zero probability that it will tunnel through the barrier and appear on the other side. This is not because it found a hidden passageway or momentarily borrowed energy from its surroundings. It occurs because the particle's wave function does not abruptly stop at the barrier. Instead, it decays exponentially through the forbidden region, meaning a tiny part of its probability cloud extends to the other side. If the barrier is thin enough, the probability of finding the particle on the far side becomes significant. The particle does not climb the hill, it simply ceases to exist on one side and begins to exist on the other. This ghostly leap is not a fringe theoretical curiosity, it is essential to the functioning of the cosmos. The fusion reactions that power the Sun and all other stars rely on quantum tunneling. The immense electrostatic repulsion between two positively charged hydrogen nuclei should prevent them from ever getting close enough to fuse. The temperatures at the Sun's core, while extreme, are not high enough to overcome this barrier classically. It is only because the nuclei have a small probability of tunneling through this repulsive barrier that they can merge, releasing the energy that bathes our planet in light and warmth. The very existence of starlight is a testament to an event that, in our macroscopic world, would be considered a miracle. Perhaps the most baffling and philosophically challenging of all quantum phenomena is entanglement, which Albert Einstein famously dismissed as spooky action at a distance. It is possible to create a pair of particles, such as photons or electrons, in such a way that their quantum states are inextricably linked into a single, unified system, regardless of the distance that separates them. For example, one can create two particles whose spins are correlated. Spin is an intrinsic quantum property, loosely analogous to classical angular momentum, which can be measured as up or down along a given axis. If the pair is created with a total spin of 0, then if one particle is measured to have spin up, the other must instantly be found to have spin down, and vice versa. The strangeness lies in the fact that before the measurement, neither particle has a definite spin. Each exists in a superposition of both spin up and spin down. Yet, the moment one particle is measured, forcing it to choose a state, its distant twin instantly chooses the opposite state. This correlation holds true whether the particles are separated by a few micrometers in a laboratory or by billions of light-years across the cosmos. The influence seems to be instantaneous, propagating faster than the speed of light, which according to the theory of relativity, should be impossible. This does not, however, allow for faster-than-light communication. One cannot control the outcome of the first measurement, it is random. Therefore, one cannot use the entanglement to send a predetermined message. The person measuring the second particle will also see a random result. It is only later, when the two observers compare their records, that they discover the perfect, instantaneous correlation between their random measurements. Entanglement challenges our deepest intuitions about space and separation, suggesting that at a fundamental level, the universe is non-local. It implies that what we perceive as separate objects can be part of a single, indivisible quantum reality, a holistic system where the concept of distance loses its conventional meaning. The quantum strangeness extends even to the nature of empty space itself. In classical physics, a perfect vacuum is the definition of nothingness, a void devoid of matter, energy, and activity. Quantum field theory, however, paints a radically different picture. At the smallest scales of distance and time, near the so-called Planck length of approximately 16 × 10^3 meters, space is not empty and calm. It is a seething, chaotic maelstrom of activity known as the quantum foam. Here, the uncertainty principle, which states that one cannot simultaneously know both the precise position and momentum of a particle, applies to energy and time. Over extremely short time intervals, the amount of energy at a point in space can fluctuate wildly. These energy fluctuations can be so great that they can spontaneously borrow from the vacuum to create pairs of virtual particles and their corresponding antiparticles, an electron and a positron, for example. These pairs flash into existence from nothing, exist for a fleeting moment constrained by the uncertainty principle, and then annihilate each other, returning their borrowed energy to the vacuum. Empty space is therefore a bubbling cauldron of these ephemeral, ghostly particles. While they cannot be directly observed because their existence is too brief, their collective presence has real, measurable effects. The Casimir effect, for instance, demonstrates that two uncharged, parallel conductive plates placed very close together in a vacuum will be pushed toward each other. This occurs because the space between the plates can only sustain virtual particles of certain wavelengths, while the space outside the plates can sustain all wavelengths. The greater pressure from the virtual particles on the outside of the plates creates a net inward force. The vacuum, therefore, has a latent energy and structure. That nothing that we perceive as the void is, in fact, a plenum, a dynamic and foundational substrate of potentiality from which reality itself arises. If the universe is so profoundly strange at its foundations, governed by superposition, probability, and non-locality, then why is our everyday experience so classical, so predictable, so sensical? The bridge between the quantum and classical worlds is a process known as quantum decoherence. A quantum system, such as a single electron in a superposition of states, can only maintain its delicate quantum nature as long as it remains perfectly isolated from its environment. The moment it interacts with anything, a stray photon of light, a single air molecule, a background thermal fluctuation, information about its state leaks out into the wider world. This interaction constitutes a form of measurement. The environment effectively observes the particle, and in doing so, it forces the particle's wave function to collapse. The superposition is destroyed, and the particle settles into a single, definite, classical state. This process of decoherence happens at an astonishingly rapid rate. A macroscopic object, like the 13-kilogram stone, is not an isolated system. It is composed of an astronomical number of atoms, roughly 10 superscript 2 of them. Each of these atoms is constantly interacting with its neighbors, with photons from ambient light, and with molecules in the surrounding air. These countless trillions of interactions per nanosecond are, in effect, continuous measurements. The quantum states of the stone's constituent particles are being collapsed so relentlessly and so thoroughly that any superposition is destroyed almost instantaneously. The stone cannot be in two places at once because the environment is constantly measuring its position, pinning it down to a single location. The classical world emerges from the quantum world not because the underlying laws change, but because the quantum effects are averaged out and washed away by the sheer complexity and interconnectedness of macroscopic systems. The solidity and certainty of our world are a consensus reality, enforced by the incessant chatter of the universe. Common sense is not a fundamental truth, it is an emergent property of overwhelming statistical noise. We return, then, to the stone, resting on the earth. Its familiar form remains, but our understanding of its existence is irrevocably transformed. It is no longer a simple, static object, but a dynamic and unimaginably complex process. Its solidity is the statistical outcome of the ceaseless, probabilistic dance of its constituent particles, their quantum strangeness tamed and averaged into predictability by the overwhelming force of decoherence. Its definite location is not an intrinsic property, but a region of extremely high probability within a universal wave function, a place where its countless particles are continuously being measured into existence by their environment. The stone's sharp boundaries are an illusion. At the quantum level, its edges are a fuzzy haze where the probability of finding its particles drops precipitously but never reaches absolute zero. There is a vanishingly small, yet technically non-zero, probability that an atom on its surface could tunnel to the other side of the planet. The stone is a local manifestation of a non-local universe, its atoms potentially entangled with particles forged in the same ancient stellar nurseries, now scattered across the galaxy. Its very substance is woven from the fleeting froth of the quantum vacuum, a temporary arrangement of fields and forces. Our perception of it, guided by the intuition chiseled into our minds by evolution, is a practical and effective tool for survival on a specific scale of reality. Common sense is the user interface for the mesoscopic world, the world of predators and prey, of falling fruit and thrown spears. It was never designed to comprehend the operating system that runs beneath. To journey into the quantum realm is to realize that the universe is not merely stranger than we imagine, it is stranger than we can imagine with the tools of our everyday intuition. It is an invitation to set aside the comfort of the tangible and to embrace a reality built not on certainties, but on a beautiful and profound tapestry of possibilities. The falling apart of common sense is not an ending, but the beginning of a deeper, more authentic encounter with the cosmos as it truly is.